Wastewater Management in Urban and Industrial Areas. Lesson 2. Economic Principles of Wastewater Management. Inflow of wastewater from economic activities causes water pollution, which affects both consumer and producer to increase cost burden, leading to reduction of social welfare. So, in order to minimize the damage due to water pollution, efficient management of wastewater inflow is needed. In this course, to understand economic principle of efficient wastewater management, principle of marginal pollution damage function and marginal abatement cost function are introduced, which leads to derivation of optimal wastewater emission. Are you ready? Through this course, you will be able to understand the concept of social welfare and explain welfare reduction due to water pollution. Also, economical interpretation of water pollution damage caused by wastewater discharge. In addition, you will be able to describe the principle of abatement cost to reduce wastewater discharge, as well as economic principle of deriving optimal wastewater emission for efficient wastewater management. So, should we begin the course? 1. Water pollution and social welfare. Available and unavailable water resources are distinguished by water quality. For example, to use remains of the river as drinking water, in order for it not to cause any harm, water quality over a certain level is required. If the water has serious quality level that cannot be used as drinking water, which is wastewater, drinking it seriously harms health and life. Not only using water resource as drinking water, using it as economic activities such as agricultural water and industrial water requires same criteria. Polluted water containing pollutants such as heavy metals and radioactivity materials cannot be used as agricultural water. Also, using wastewater mixed with waste oil as industrial water for cleaning parts at automotive factory is impossible. In conclusion, economic entities utilizing water resources are affected by water pollution degree of water resources in terms of welfare directly and indirectly. Unpolluted water could be used as factors of production of economic activities or could be used directly to increase welfare. In same circumstances, polluted water, which is wastewater, could harm consumers' health or cause loss of producers to decrease welfare. Then, how can welfare of economic entities by water resource usage could be measured? Welfare earned by consumers could be presented by health status, possibility of survival and death, satisfaction, and other various benefits. Welfare earned by producers is measured from factors containing its profits when used as a factor of production, and all other economic profits. An easy way to measure social welfare in economical perspective is to exchange index to currency units. This is done by introducing consumer perspective of consumer surplus and producer perspective of producer surplus. Should we take a closer look for better understanding? Consumer surplus is consumers' willingness to pay minus the actual payment. Here, surplus means that something is left. So consumer surplus is the surplus of benefits that consumers gain when they use water resources. To understand this intuitively, let's look at the following graph. On the screen, vertical axis P is water resource price. Horizontal axis Q is water resource usage. Line drawn on it is demand curve for water resource. In general, the demand curve is consistent with consumers' marginal willingness to pay or marginal benefit. Now, let's suppose that the consumer pays a price of P star and demands water resource as much as Q star, moving water resource to Q star. Total willingness to pay gained by consumer or total benefit earned is area beneath MWTP from 0 to Q star. Mathematically, this area is a value of integration of MWTP from 0 to Q star. However, Through this process, did consumer use water resource for free? No. They used by paying the price of P star per unit, paying P star times Q star amount as total. Geometrically, consumer surplus, CS, is removing total payment from total benefit to result in remaining triangle. Now, we should look in producers' perspectives. Producer surplus is derived when producer sells a product by its revenue minus the total cost. Residual is the producer's. You did not get it? Let's look at the graph again. To make our discussion easier, rather than selling the water resource directly, let's assume that producer produced products by using water resource as producing factor. Here, water resource used as input is horizontal axis Q, and price of water resource is vertical axis P. Line drawn on graph is marginal cost, MC, related to producer's water resource. Supply curve equals the marginal cost curve, and it is represented as S equals MC. When producer used Q star of water resource to produce products, and price per unit is P star, water resource revenue from total revenue is area of rectangle, which is P star times Q star. But did the producer earn revenue for free? Of course, no. Cost of water resource used as input factor during producing has been paid, and that is total cost, area beneath marginal cost curve. As marginal cost is derived by taking derivative of total cost is derived by integrating of marginal cost from 0 to Q star. In this case, producer surplus is derived by considering revenue from water resource, which is the area of rectangle P star times Q star. After removing total cost, the area beneath marginal cost. Producer surplus is the remaining area, the red triangle. Assuming that the economic entities of society consists only consumer and producer, social surplus is derived by adding consumer surplus and producer surplus. Namely, using water resource with price of P star for amount of Q star, like shown in the figure, welfare of the whole society is calculated as the area of triangle, adding consumer surplus and producer surplus, and which we call social surplus. When water pollution happens by inflow of wastewater to usable water, original P star changes even if same Q star amount of water resource is used. This is because that the price may change due to value change caused by water pollution. In this case, CS and PS are recorded elsewhere than equilibrium point. Social surplus, the sum of two, shall decrease. Why is that? Welfare, represented by social surplus, is maximized at equilibrium point, where supply and demand meets. And it fails to maximize when oversupply or overdemand occurs. 2. Water pollution damage. Determining the relationship between water pollution and welfare change can be done other than focusing on consumer surplus, producer surplus, and social surplus. What is it? It can be done by focusing on wastewater emission to directly understand the impact of water pollution caused by wastewater emission on social welfare. When wastewater from economic entities inflows to surface and groundwater, water quality pollution would occur. Damage to people and ecosystem when this happens is called water quality pollution. When damage by water quality pollution is converted into monetary unit, it becomes easier to interpret in economic point of view. This conversion is called the damage function. Wait a second. There are two things to consider as index representing water quality pollution. One is emission of water pollutant, and another is water quality pollution. First, considering the emission of water pollutant, damage function shows the relation between wastewater emission and damage. When water quality pollution is considered, damage function shows the relation between cumulative pollutants in the ecosystem and damage. Water pollutant emission and water quality pollution, with these two indexes of criteria. When wastewater emission or pollution due to wastewater is increased by 1 unit, the additional damage is called the marginal damage, and damage caused by wastewater emission or pollution at certain level is called total damage, which is sum of marginal damage at that level, total area of marginal damage. Shape of marginal damage curve normally has a positive relation of increasing as emission increases, and various shapes are available depending on the type of water pollutant. Should we take a moment to take a look at the marginal damage curve depending on the type of pollutant? Left shows the weakly toxic wastewater, and the right shows the strongly toxic wastewater, the chemical wastewater. First, in case of weakly toxic wastewater, when emission is small, pollution damage is also small. And as it gets larger, it rises dramatically. It occurs in gray water or black water, which is household wastewater. In case of strongly toxic wastewater, toxic chemical wastewater could result in large ecosystem damage with small amount. Marginal damage is positive, even if emission is close to zero. For example, heavy metals such as phenol and radioactive dissolved in nuclear accident. Marginal damage curve shows different shapes depending on the type of pollutants, but also on spatial and temporal environment. For example, when same amount of wastewater is discharged on the river, in the summer, when precipitation is high, we'll experience less damage than in the winter, with low precipitation. Also, region with low-density population should experience more damage than region with high-density population. 3. Abatement and abatement cost. Previously, we provided an example of water pollutant emission and wastewater quality pollution used as measure of water pollution damage change. In this case, vertical axis is represented as marginal damage. But as a new measure, we could use a concept of abatement. Wastewater abatement means the reduced wastewater emission from the source. To be specific, wastewater abatement is wastewater emission from the source without the environmental policy minus the actual wastewater emission with environmental policy. Using wastewater abatement, vertical axis is not marginal damage, but marginal benefit. Marginal benefit occurs when wastewater emission is reduced by 1 unit. When wastewater emission is reduced by a unit in high level of emission, marginal benefit increases. As emission reduction is increased, marginal benefit decreases, showing negative relation. Wait a second. You do not understand the negative relation? We should think of the extreme cases. Consider a serious wastewater emission. If wastewater reduction is done for a unit, people's marginal benefit should be large. For example, when stinky wastewater emission is done near the rivers, if the factory stops for 1 day, people suffered from smell should benefit a lot to experience a large marginal benefit. But if the reduction continues to reduce pollutants when wastewater emission is stopped near the rivers for days, even if factory stops for another day, people suffered from smell should benefit a little. Now you get it? Pop quiz. Please read the following question and select O if it is correct and X if it is wrong. Let's consider a cost related to reducing wastewater. Cost when the source reduces wastewater emission to response environmental polity is abatement cost. Like damage function is distinguished into marginal damage and total damage, abatement cost function is also distinguished into marginal abatement cost function and total abatement cost function. Marginal abatement cost could be represented in 2 ways, as in the screen. Graph on the left shows the case of horizontal axis with abatement. Generally, abatement cost increases as abatement increases. It shows a positive relation. On the other hand, on the right, when horizontal axis is emission, it shows a negative relation. But different cases of abatement and emission showing different relation may not be understood at once. Changing the way of reading the graph from left to right, let's read it from the right to left of the horizontal axis. Right side of the horizontal axis shows large emission. Decrease of emission means increase of abatement. So, as abatement increases, marginal abatement cost increases. As emission decreases, marginal abatement cost should increase. Not so difficult now, isn't it? Total abatement cost is derived from the area below total abatement cost curve. Like relationship between consumer surplus and producer surplus, or marginal damage and total damage, total abatement cost is derived by integrating marginal abatement cost from zero to certain value. 4. Efficient management of wastewater. Now we will take a look at how to derive optimal wastewater emission and abatement with marginal damage and marginal abatement cost. For your better understanding, we should draw marginal abatement cost and marginal damage in one graph. In case of horizontal axis with emission and abatement. First, with left graph, setting horizontal axis is wastewater emission. We will see how optimal wastewater emission is derived. Setting wastewater emission as E and optimal wastewater emission as E star, E star is derived at the point where marginal damage due to wastewater emission is as same as marginal abatement cost to reduce wastewater emission by 1 unit. In the graph, it is the point where marginal damage curve and marginal abatement cost meets. How can we tell that the solution is optimal at meeting point? Area below marginal damage and marginal abatement cost represents total damage and total abatement cost. In the graph, when wastewater emission is E star, the area of total damage and total abatement cost is minimized, and it leads to the most socially desirable level. To minimize the damage and the cost. For example, let's take a look at the case when emission is larger than E star. If emission is larger than E star, marginal damage is larger than marginal abatement cost for unit of emission reduction. Calculating the area below, it is even larger than the E star level area. Reducing emission leads to damage and cost reduction and social welfare increase. But, in contrast, when emission is less than E star, marginal abatement cost is larger than marginal damage. With similar logic, total area below is larger than E star level area. So, increasing emission is required, since society is in inefficient state. This graph could be explained in a similar way. In this case, aware that horizontal axis is abatement, A, so that the optimal wastewater abatement is A star. When horizontal axis was emission, the graph was composed with marginal abatement cost and marginal damage. In case of abatement, it is composed with marginal abatement cost and marginal benefit. And the optimal wastewater abatement, A prime, is the point where marginal benefit curve and marginal abatement curve meets. Quiz! Let's check what we've learned through a quiz. 3 questions will be given, and you will have 2 chances. Then let's start. Summary. Let's review and summarize what we've learned so far. We learned about economic principles of wastewater management this time. Next time, we will learn about environmental policies for wastewater management. Thank you very much, everyone.